Hello students, today we will discuss compactness in topological space. Before that we consider compactness in real line when x is equal to r. In real line set is said to be compact if it is closed and bounded. Number 2, if every sequence has a convergent subsequence and that limit belongs to that set, then we say that set is compact. Second way, by considering a sequence, from this sequence if we are able to draw a convergent subsequence and the limit of that sequence belong to the set, then we say that set is compact. Third, the compactness in a real line can be seen if every open cover has a finite subcover, then we say that set is said to be compact. Now we come to compactness in metric space. In real line compactness, when a set is closed and bounded, in metric space this will not happen. If a set is closed and bounded, then we cannot say that set is compact in the sense of metric space. For this we can take, suppose X is an infinite set, and we define a discrete metric on that set 0 if X is equal to Y, 1 if X not equal to Y. Here this set is closed and bounded, but this is not compact because it is closed, because it has no limit point. So its derived set is empty, and the open set of this consists of, if you draw a sphere with center epsilon and radius x, and then singleton or either singleton or whole space, a whole set, provided epsilon is less than equal to 1 or epsilon greater than 1. It is closed, it is bounded, but it is not compact. Suppose it is compact. If it is compact, then we can, for taking epsilon is equal to half, we can write X as union of I1 to K, a sphere with center xi radius half, and here the set is of singleton and it will come x1 to xk, and this is x. Here this x is infinite and this is finite, so a finite set cannot be equal to infinite set, so a closed and bounded set in metric space cannot be compact. A simple example. Now compactness in topology in metric space we will deal with by considering if every sequence has a convergent subsequence. If we can draw a sequence and from that sequence if you draw a convergent subsequence, every sequence has a convergent subsequence, and that sequence converges into that set, then we say that metric space is compact. Second, if every open cover has a finite subcover. So mostly in metric space we will deal with every sequence has a convergent subsequence, or if every open cover has a finite subcover. Now we come to in topology. In topological space, we are not always able to find a useful metric on a given set, then we will take the help of topology. In topology, we will consider the collection of subsets, and that collection of subsets form open sets. So it is not always possible to find a useful metric on a given space. So instead of that, we take collection of subsets, and that collection of subsets can be dealt in topological space. So in a topology, compactness is defined in terms of open cover. Compactness in topology is defined in terms of open cover. If every open cover has a finite subcover, then we say that that set is compact in a topological space. So we have discussed compactness in real line by taking a set is closed and bounded if every sequence has a convergent subsequence, if our open cover has a finite subcover. In metric space, we deal with compactness if every sequence has a convergent subsequence, then that element converges, then the limit element belong to that set, and every open cover has a finite subcover. But in topology, we will deal with every open cover has a finite subcover. Now we come to cover. Let X be a set. We are defining on a set what is cover. Let X be a set. A be a subset of X. Now, a collection be denoted by C. A collection G lambda belong to gamma. Gamma is index set. This collection is said to be cover of A if A is contained in union lambda belong to gamma G lambda. X be any set. A be subset of X. C is the collection of subsets of X. Then this collection is cover of A if A can be written as union lambda belong to gamma G lambda. Now, if X is topological space and this X is topological space, and now this collection is a collection of open sets. If A is contained in union G lambda belong to gamma, then we say G lambda is open cover of A. Then we say if G lambda is open, then this is open covering. Okay. Now, if A is a subset of X, X is topological space, then A has an open cover if A can be written as in this way. If this cover has a finite subcover, then we say that this set is compact. Finite means A can be written as union I 1 to n G lambda I. If this cover has a finite subcover, when we talk about, if you take any cover and every cover has finite subcover, then we say that set is said to be compact. Now we come to when a space is said to be compact. When we say a space is said to be compact, then how we define cover? When a set is said to come, suppose X is a set, X is space, topological space. In fact, X is a topological space, and G lambda belong to gamma be a cover of X. Then X can be written as union lambda belong to gamma G lambda. When we consider the space, then this cover, then this collection of subsets of X covers X if X can be written as, when we consider A is a subset of X, then this collection is cover of A if A can be written as union lambda belong to gamma G lambda. Because here we will observe that if you write it X, this G lambda belong to gamma is cover of X, then by definition this can be written as union lambda belong to gamma G lambda, and it is always union lambda belong to gamma G lambda is contained in X. So here, combining this, you can write X is union lambda belong to gamma G lambda. When we consider space, this cover can be written in this form. When we take a subset, a subspace, then this can be written in this form. Now we come to definition of compact. set. Let X be a topological space, A be a subset of X, then A is said to be compact if every open cover of A has a finite subcover. Now we have to compact space. Compact space. Let X be a topological space. The space X is said to be compact if every open cover of X has a finite subcover. Now we come to some examples of compactness. Every finite set in a topological space is compact. Every finite set in a topological space is compact. Let X be a topological space. A be a finite subset of X. A be a finite subset of X. Now, A is finite. Suppose A is of the type A is finite set. Suppose it is a finite number of elements. Now, first we have to take its cover, and from its cover we have, if you are able to draw a subcover, then we say that A is compact. Now, let C be the cover of A. C is equal to G lambda, lambda belong to gamma, be an open cover of A. If it is open cover of A, then by definition A can be written as union lambda belong to gamma G lambda. Now here A has element, and then x1, putting the value of A, x1, x2, x3 and so on, xn, these are contained in union lambda belong to gamma G lambda. Now we pick up first element. This first element is contained in some open set. Suppose x1 belong to G lambda 1, x2 belong to G lambda 2 and so on, xn belong to G lambda n. Now we add all these elements. This x1, x2, xn, these are contained in G lambda 1 union G lambda 2 and so on G lambda n. Now this is A. This is A is contained in union I1 to n G lambda I. Now we have drawn a subcover because we have the A union. This A is contained in union lambda belong to gamma G lambda. This is the cover of A, and we draw a finite subcover. Hence we say that a finite set is always compact. Now we will come to another example, an indiscrete topology. Indiscrete topological space is always compact. Suppose X is an infinite set. X is an infinite set. Now take the topology phi and X. Now this X is covered by we have only two open sets, phi and X. X is covered by only one open sets, then it is finite. X is covered by only one open set, that is X. So it is finite cover. So we say that indiscrete topology is always compact because X is covered by only one set, that is X itself. Now we come to discrete topology. Discrete topological space is not compact. Discrete topological space. Suppose X is an infinite set. X is a infinite set, and in case of discrete topology, T phi, or collection of R, we denote rho x, power set of x, the collection of all subsets of x. Here we observe that x can be written as union of all singletons. X can be written as union of all singletons, because power set में in case of discrete matrices singletons are also open set, then x can be written as union of all singletons. If from this union of singletons, if you remove some open set, then x cannot be, if you remove some singleton from here, then x cannot be equal to union of these singletons. So this cover has not finite subcover, because whatever may be the cover of x, then every cover has a finite subcover. We choose one cover this. If you remove some elements, then x cannot be this equal to this, because x is infinite and this union is finite, then they cannot be equal. So discrete topological space in can x is infinite, it is not compact. When x is finite, it is compact, because these number of elements in the subsets are finite. The x can be written as union of finite set, and finite set is always compact. So when x is infinite, in case of discrete topology, it is not compact. When in case of indiscrete topology, when x is infinite, it is always compact. It may be compact, it may not be compact. Discrete topology can be compact when x is finite, and discrete topology is not compact when x is infinite. Now we come another example. Now we come to every theorem, every cofinite topological space, every cofinite topological space is compact. Proof. Let T be a cofinite topology. We can write as phi g lambda is a subset of x such that g lambda complement is finite. Now we want to prove this cofinite topology is where x is infinite set. X is infinite set. When x is infinite set and there is no empty, and the topology, cofinite topology is the form phi g lambda containing x such that g lambda is finite. Now x can be written as g lambda is open, g lambda is finite. X can be written as, you can observe from here, x can be written as g. We want to prove every cofinite topological space is compact. So first we take its cover. Let C g lambda belong to gamma be a cover of x. Whenever we want to prove a set is compact, first we take its cover. From that cover we draw a finite subcover, then we say the compact. So first we consider here cover, the cover of cofinite topology. Let C be the cover of xt, because it is a space. So x can be written as union lambda belong to gamma g lambda. Okay, because it is cover. If it is subset, it is space. So x, it is written as x is equal to. If it is a subset, then x contained in. Now we further observe x can also be written as g lambda union g lambda complement. Now this is finite. G lambda is here finite. Here g lambda is finite. So we can write here x also can be written as g lambda union g lambda naught finite for some lambda naught belongs to gamma. Now we have already said x has a cover, so x can be written as union lambda belong to gamma g lambda. So this can be written as union lambda belong to gamma G lambda. This is equal to G lambda union G lambda complement. Now from here we observe that G lambda naught complement is contained in union lambda belong to gamma G lambda. This, or further we can write it as x minus में G lambda by definition of from set theory, x minus में G lambda is contained in union lambda belong to gamma G lambda. Now G lambda not complement is contained in union lambda belong to gamma G lambda, so G lambda not is contained in, because it is a finite, so it is contained in finite sets, so say G lambda 1 union G lambda 2 and so on union G lambda n, because it is a finite G lambda not complement. Now this can be written as x minus में G lambda naught is contained in G lambda 1 union G lambda 2 so on union G lambda n. Now x can be written as union G lambda naught union I1 to n G lambda I. This is this thing. So we have assumed x has a cover, x is equal union lambda belong to gamma G lambda. This is the cover of x, and from this cover we draw a finite subcover, so we say that cofinite topological space is compact. Now we come to next theorem. Usual topology theorem. Usual topology is not compact. In usual topology, that we open sets are in fact the intervals, and they are of the form A, B, such that A and B belongs to R and A less than B. These are open set. Intervals are in fact open set in usual topology. Now we have to prove where x is equal to R. Here x is equal to R. X is equal to R. You take here x is equal to R. Now we have to prove it is not compact. Here we take a cover, and from this cover we will show that we are not able to drive finite subcovers. Suppose C is the cover of R. AI, BI, AI less than BI, AI and BI belongs to R. Suppose C is the cover of R, that is R can be written as union over I, AI, BI. Now we show that R has no finite subcover. Suppose R has a finite subcover, that is A1, B1, A2, B2, and so on, AN, BN be the finite subcover of R. Then R can be written as union I1 to N AI BI. Now let K be the maximum of all ai bi. K is the maximum number, a real number, the maximum of all these. Then is union I want to n ai comma bi is contained in minus k to k. So R is contained in this. It is impossible because k is a number and R is a real number. A real number cannot go to a set, open set having finite when k is finite. So we cannot say this implies R is contained in minus k to k. Suppose here k is 100, then if you want to take an element 200, then it cannot goes to that. So usual topology is not compact. Now we come to another theorem. Next theorem is every closed subset of a compact topological space is compact. Proof. Let Xt be a compact topological space. Let B be a closed subset of X. We want to prove B is compact. To show B is compact, first we take its cover, and that cover we draw a subcover. Let C is equal to G lambda. Lambda belong to gamma. B cover of closed subset of B. So B can be written as, by definition of cover, union lambda belong to gamma G lambda. Further, X can be written as B union B complement. Now putting the value of B, this is contained in union lambda belong to gamma G lambda union B complement. X is contained in this, but X is given to be compact. X is compact. So X has a finite subcover. So X can be written as union. This is a cover of X, and this cover is a finite subcover. So we can say X is equal to union I1 to N G lambda I union B complement. But X is B union B complement. So this is further contained in putting the value of X B union complement union I1 to N G lambda I union B complement. Now from here we observe this is B complement, here B complement. From here we observe B is contained in union I1 to N G lambda I. Now B union lambda belong to gamma G lambda is the cover of B. From this cover we are able to draw a finite subcover. So we say a closed subset of a compact topological space is compact, but if the set is not closed, a subset of a compact topology need not be compact, but a closed subset of a compact topological space is compact. Now we come to next theorem. Theorem. Continuous image of a compact space is compact. Continuous image of a compact space is compact. Proof. Let F be a continuous mapping from one topological space onto another topological space xt to yt star. Now, continuous image of a compact space. Now, X is compact. X is given to be compact. We have to show y is equal to fx is compact. To show y is equal to fx compact, we take first its cover, and from that cover we draw a subcover. Let C is equal to G lambda, lambda belong to gamma, where gamma is indexed, be a cover of y. Now this is the cover of y. Here you note that y is a space, so y can be written as this is, we here equal to a symbol, we have symbol of equal to, y is equal to union lambda belong to gamma g lambda, but y is equal to fx, fx is equal to union lambda belong to gamma g lambda. F is continuous mapping, so x can be written as f inverse union lambda belong to gamma g lambda. By set theory, you can also write it as x union lambda belong to gamma f inverse g lambda. X is given to be compact, so it has a finite subcover because X is compact. So X is equal to union lambda belong to gamma f inverse g lambda, but X is given to be compact, so it has a finite subcover. So X can be written as X is equal to union I1 to n f inverse g lambda I, because X is compact, so it has a finite subcover. Or this can be written as, due to continuity, f inverse union I1 to n g lambda I. Further, this implies fx is equal to union I1 to n g lambda I, and fx is equal to y is equal to union I1 to n g lambda I. Now you observe y is equal to union lambda belong to gamma g lambda is a cover of, and we draw a subcover, a finite subcover of y, such that y is can be written as union I1 to n g lambda I. Hence continuous image of a compact space is compact. Now we come to next theorem. Continuous image of a compact set, okay, compact set is compact. Continuous image of a compact set is compact. Continuous image of a compact space is compact. Here we are proving continuous image of a compact set. compact set. In the last theorem we proved continuous image of a compact space. This is the basic difference. Proof. Let F be mapping from one topological space to another topological space. F be on to mapping from one topological space to another topological space. Let A be a compact set of X, or we want to show f of A is compact. To show f of A is compact, first we take its cover. Let C G lambda belong to gamma be cover of A, cover of f of A. So f of A can be written as union lambda belong to gamma G lambda. From the set theory we know that A is contained in F inverse f of A. So this can be further f of inverse f of A. So this is further contained in f of inverse f of A union lambda belong to gamma G lambda. This implies A is contained in f inverse union lambda belong to gamma G lambda. Or further, we are given A is to be compact, and this is the cover of A. A is to be compact, so it has a finite subcover. So this implies, or further you can write A is contained in union lambda belong to gamma f inverse G lambda. But A is compact, so it is a finite subcover, so A can be further written as union I1 to N f inverse G lambda I, because A is compact. Or we can write it, this is equal to f inverse union I1 to N G lambda I. The f is continuous, so f of A can be written as, this is contained in union I1 to N G lambda I. Now this is the cover of f of A, and we draw a finite subcover of A. So we have shown that continuous image of a compact set is compact, and we also proved continuous image of a compact set is compact. So this is only the basic difference in both. First we proved continuous image of a compact space, and here we have proved continuous image of a compact set. There is a difference between both these theorems.